Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. This is a continuation of the previous lecture. Now in lecture 21, we are going to discuss in detail about the design for blast. It's a sequel lecture where about 4 lectures in continuum will be discussed about the design procedures used for design of systems under blast loads. There is a handbook for design of structures under fire and blast loads published by me and Pratibha. Please have a look at this. The detail is available here, which is published by Cambridge Scholars Publishing UK. You also have other references as listed here: fire resistant design of structures and design aids for offshore structures under special environmental loads including fire resistance. So friends, these 3 are very important reference for the sequel of lectures now on this course. Welcome to lecture 21, Design for Blast, sequel lecture 1. Friends, let us first ask a question: how design for blast is different from conventional other design forces? If you talk about blast resistant design, Now, most importantly, the geometry and the spatial layout of the structure influences the blast loads. So, in blast resistant design, first option is to control the geometric layout and the spatial, that is vertical and horizontal spreading of the structural system to mitigate or to reduce the effect of blast on structures. Therefore, friends, the first advice could be a well designed architectural layout can be the first step towards blast resistant design. You may wonder how maritime structures are involved in architectural layout. We already discussed about that maritime structures, as you go deeper for offshore platforms, they are usually form dominant. Therefore, arrangement of structural members and integrating them to a structural system becomes a very important factor, and now that factor also plays a role in mitigating or reducing the effect of blast on these structures. So, what is the advantage when you have a well designed architectural layout? The well designed architectural layout will help us to reduce the intensity of blast. Therefore, it helps to improve structural resilience. So, that is the fact here. See, effective risk mitigation actually starts at the planning stage. So, effective risk mitigation for blast loads starts at the planning stage. The integration of passive design strategies such as security, deception, shielding plays a very important role. Let us see what are these in detail. For blast loads, as we said, the geometric design plays a very important role. Structure should be monitored for potential human threat. Deception is to conceal the vital features of the structure and lead to a wrong focus. This is useful even if attacks are successful. Structure should be monitored for the potential human threat, and shielding is to protect structures from providing physical barriers. Examples could be blast walls, bollards, anti-ram components, control for vehicle and pedestrian entrance, and natural land formations. Therefore, friends, by design and by planning them, one can always make an effective approach for blast resistant design. So, by design, distance between the potential charge and the target should be separated well apart. So, design should be carried out for potential blast loads only. So, the first step in blast resistant design is to make a design effective, which is creating good deception, good shielding effects, and also isolating the structure far away from the target of potential blast loads. Having said this, so blast sources should be from the spherical explosives and non-spherical charges. So, before that, let us see There are some terminologies which are useful in blast resistant design. First, let us talk about what is a standoff distance. Standoff distance by design is the space between a potential explosive and the structure. And ideally speaking, for good design, this distance should be maximized. Larger distances reduce the peak overpressure. So, larger standoff distance help us to reduce the peak overpressure and therefore, it can reduce the impulse caused by the blast load. Therefore, the structure should be explicitly designed for blast loads if threat assessment identifies a credible risk. Now, let us try to understand the blast source. To design a structure for a blast resistance, one must first understand the origin of the blast. So, the origin of the blast is referring to the explosive charge and how this charge is configured in space. You can do this in three scenarios. Three scenarios are expressed in the literature. They are classified based on the location of detonation with reference to the site of interest. One is what we call spherical explosive, other is hemispherical burst, third one is air burst. Let us see one by one. So, what you see in the screen is the figures of spherical explosive or spherical burst, hemispherical surface burst and air burst. The spherical burst is also called as free air burst, whereas hemispherical burst is called as a surface burst, and of course, the third one is the air burst. Let us see these three of them in detail. Let us first talk about the spherical explosive. Or the spherical blast. These explosives spread the blast loads on all directions. When detonated, they generate a symmetric shock on all directions, outward, on all directions. Equally. This type of blast is easy to model. And is commonly used in design charts. Okay, and simulations. What you see is actually this one. So, this is a numerical model of a spherical blast. So, from the source, it blasts spherically in all directions symmetrically outward. Okay. So, this is an horizontal distance what it can cover, and this is a vertical or normal distance what the blast can cover, and this becomes the slant distance what the blast can cover from the source, from the ground. So, this is a very simple numerical model which helps us to model the spherical burst which can happen uniformly in all directions. The next one is the non-spherical charges. The non-spherical charges include elongated, irregularly shaped, or even sometimes layered explosives. Their blast effects are more complex. And they do not spread energy uniform in all directions. So, the pressure distribution is not uniform in all directions. The scenarios require very detailed analysis, especially when the scaled distance is very small. It requires a detailed analysis. Now, let us talk about the detonation scenarios as free burst. As I said, the spherical burst, the free burst, where it can spread uniform all around. The next one is hemispherical surface burst. Where the explosive is placed on the ground surface. And effectively spreads like a rigid reflector. This scenario produces stronger reflected pressure waves in comparison to the free air burst. The shock wave reflects off the surface and combines with incident wave, leading to higher peak overpressure. It can affect very severely the nearby structures. The third one, of course, is called the air burst. Air burst occurs when the explosive detonates at an elevated position from the ground. The reflected wave from the ground interacts with the incident wave at certain angle, forming a Mach stem. This interaction leads to complex wave pattern and it impacts wider area. Airbursts cause significant effect on multiple elevations. Of a structure and produce large slant range effects. Let us look at this model which you see on the screen. This is an hemispherical blast which is shown on the screen here, where the assumed wavefront is parabolic and the reflected wave spreads horizontally and not directionally like this. Whereas in airburst, the source of detonation happens at a height from the ground and it affects building at different elevations. So, this has got more serious effect compared to the free airburst. Okay, this is also an airburst, but this has got more serious effect because it creates a slant effect on the buildings at different elevations. Okay. So, these are the three types of blast scenarios which can happen, for which the design has got to be carefully done. Now, let us talk about some key terminologies involved in blast designs. So, the first terminology as we see is called as a standoff distance. Standoff distance is that distance between the center of detonation and the point of interest. Look at this figure. If I want to find the standoff distance of a point on the front face, I must drop a perpendicular of that point to the ground and measure the distance normal from the detonating source. So, this becomes my standoff distance, which is square root of sum of squares of this value and this value. If you want to measure the standoff distance for any source on the side of the building, then it has got two values. One is the distance of the point on the same plane plus the distance on the side, R1 plus R2. Whereas, if you want to find the distance on the top face, then you project the point on the surface, drop it down to the ground and get this value. So, now this becomes the hypotenuse distance of this square plus this square. Add that R2 here. So, in the front face it is only R, in the side face it is R1 plus R2, in the top face it is R1 plus R2. Therefore, the effect of standoff distance is larger on the top face. So, the more the standoff distance, because standoff distance is the distance between the point center of detonation and the point of interest, the more the standoff distance, the effect of blast is lesser. So, if you have a source of blast on the ground, you will notice that the front face will have the maximum effect, side face lesser and the top face the least, if the source is on the ground. If the source is an air spread model is happening at an elevation here, then the standoff distance reduces. Therefore, the effect of this blast on the structure could be more. So, very importantly friends, the first terminology what we are interested in blast analysis is the standoff distance, which tells me directly the effect of blast on the structure. Second point is what we call as the close-in detonation. So, before we move on to the close-in detonation, let us talk about the standoff distance in different cases. Let us say I take an example to compare the different effect of blast explosion. Let us say the standoff distance can be also accounted to what we call the scaled distance, where the scaled distance is given by Z as R by W to the power 1 by 3. Now, where Z is the scaled distance, in meter per kg to the power 1 by 3, R is the actual distance from the explosion to the point of interest. So, we can say this as the stand-off distance expressed in meters, and W is the explosive mass. We have already learnt in the previous lecture, we express explosive mass in TNT equivalence. Okay? So, the scale distance helps us to know the effect of the blast on the building. So, one can use the blast charts and governing equations to find the effect of blast if scaled distance is known, because from the scale distance one can compute the peak overpressure caused by the blast. From the peak overpressure one can find the effect of blast on structures and human. I think we have shown a table in the last lecture, one can use the same table here. Okay. Let us move on to what we call as close-in detonation. Close-in detonation is a very simple term, refers to detonation occurring at a scaled distance below which the blast pressure distribution is non-uniform. So, what is the distance? It is that distance which is lesser than 1.2 m kg 1 power 3. So, it is a very close distance where the detonation or the effect of blast will be more severe. Far field detonation refers to detonation as a scaled distance above which the resulting blast pressure distribution is uniform over the reflecting surface. So, when the close-in detonation which becomes very lesser scaled distance value, then the pressure distribution on the reflected surface becomes non-uniform. If it is far field, then it becomes uniform and the scale distance is greater than 1.2 meter per kg root 3. Okay. So, stand-off distance can be used to convert or to compute the scale distance. From the scale distance, I can always say whether the detonation is close-in detonation or far field detonation, because if the scale distance is lesser than 1.2 mass per kg meter per kg, if the scale distance is less than 1.2 meter per kg to the power 1 by 3, then it is referred as close-in detonation. So, the effect or the consequence is going to be very severe. If the scale distance is more than 1.2 meter per kg to power 1 by 3, then I can call this as far field detonation. So, friends, to know the qualitative effect of detonation or blast on a building or structure, scale distance is used, and scale distance can be computed if you know the stand-off distance using this equation. Okay. Let us move on to what is called as a Mach number. We already know this in different field of engineering, but let us talk about what is Mach number here. Mach number m is the ratio of speed of shock waves to the speed of sound. It is a ratio between two speeds. A Mach number greater than 1 implies supersonic condition. Okay, let me write down that here. A Mach number greater than 1 indicates supersonic sound conditions. We already spoke about scale distance. We already spoke about TNT and its equivalence in the previous lecture. Just for continuation, explosion damage is estimated using something called TNT equivalence method. TNT is trinitrotoluene, an important explosive given by this equation. TNT can very quickly change its composition from solid to an fast expanding gas. Therefore, it is one of the dangerous explosive which can cause devastation to buildings. Okay. When TNT detonates, it rapidly changes from solid to hot expanding gas and it releases larger amount of energy. Okay. It releases larger amount of energy and this rapid energy causes blast wave. The strength of other explosives is measured in TNT equivalence mass, which helps in comparing their damage potential. TNT is widely used in blast analysis due to its well understood behavior and energy output. It is considered as an ideal reference material for estimating explosive damage because of two important chemical reasons. One is the energy release from stable end products. TNT is an explosive because it contains elements of carbon, oxygen, nitrogen, which means that when it burns, it produces highly stable substance. They are chemically unstable, which means that it does not require much force to break their bond. So, plastic explosions comprise of explosives mixed with oil or plastic resistance are called RDX. Now, if you look at the energy release from a stable product, let us talk about an equation which has the TNT explosive. So, the equation of TNT combustion can be written as nitrogen O6 when it yields to nitrogen plus carbon monoxide plus steam or hot water vapor plus carbon, which is a soot, black powder. So, this can rapidly expand and it is stable. It requires very less force to break this bond. Therefore, it is one of the standard referral explosive used for computing the damage equivalence. So, chemical instability and energy release as a stable product. Are two important key factors making TNT as a referral explosive. Okay. So, we work out all explosives as equivalent TNT to compare the damages caused by that explosive compared to that of TNT. Okay. Having said this, let us now talk about blast wave propagation. Before that, let us try to understand how do we compute the damage from the blast loads, which was explained in the previous lectures as well. Let us rewind this. To compute the damage from blast loads, the first step is to compute the flammable inventory, which is the total mass causing the burning. Once it is done, we compute something called scaled overpressure for the chosen scale distance. So, scaled overpressure can be computed from this, the peak overpressure. Once the peak overpressure is computed, I can always use this table. If you know the peak overpressure, I can always use the corresponding table to compute the damages. So, let us look at this table where the equivalent TNT mass of different explosives are given. Let us say if you take about ammonia dynamite, gelatin, TNT, RDX, etc., their corresponding density, equivalent mass participation and the equivalent mass for impulse are available in this table. So, if you look at this table, TNT is taken as unity for comparison. So, compared to TNT, they are all given in fractions. Okay? That is why we call TNT equivalence is being used. Now, if you look at the performance of structures under blast loads, they are based on classification of structures. The classification does not bear importance. So, the building can be categorized as low, medium and high importance, whereas residential buildings are taken under low importance with occupancy less than 50. With more than 50, they come under the following of medium category. Public buildings such as schools, offices, cinema halls, industrial buildings come under medium, and maritime structures, strategic structures, offshore structures, financial establishments, lifeline structures all come under high importance. Okay? So, we can also categorize the building depending upon its occupancy level, then we work out on this. Having said this, let us now move on to what is called threat assessment. Threat assessment is carried out to determine all potential sources of detonation. It shall identify two parameters related to blast load estimates. One is the charge mass and the stand-off distance. If you know the potential charge mass and the stand-off distance of your source from the target, then one can compute something called the threat caused by that explosive onto the building. If threat assessment identifies multiple sources of detonation, the effect of blast on all structures shall be assessed, considering them individual, and whichever combination gives you the worst scenario, that will be considered as a serious threat. Therefore, structure should be designed for a worst scenario compared to all of these. Let us look at this figure and try to find out how the blast wave behaves with time. So, this figure tells me a plot of pressure versus time respective y and x axis, as you see here. So, the reflected overpressure which travels from an atmospheric ambient pressure, it rises to its peak value, which is called reflected overpressure at arrival time t. Once the arrival time is reached and the peak reflected pressure is reached, then the pressure drops. Okay? This is called positive reflected impulse, IR. It drops at a positive duration T naught, then before it reaches atmospheric or ambient, it creates a negative effect. So, it is called negative impulse. So, pressure waves create two impulses. One is the positive impulse because of reflected impulse. The second one is a negative impulse. The more serious is a negative impulse, not because the magnitude is lesser, it is because the duration is much larger compared to this. Okay? It stays for a longer time compared to this. So, this creates a suction pressure which causes more damage to structures. Okay? So, now the incident and reflected blast waves vary as follows. You can always find the variation of peak overpressure with this value as a function of time, which is given by this relationship, where P naught is the peak blast overpressure, same as the peak incident and reflected pressures, okay, same as this. Alpha is called the decay coefficient and T naught is called the positive phase duration. So, T naught is the positive phase duration, which is usually small compared to the negative duration. Okay. Having said this, so now we understood that the positive phase of this wave is defined by pressures above atmospheric. This phase is responsible for major portion of the blast damage. Okay. Following this, the air pressure drops down below ambient, creates a negative pressure or what we call suction effect. Though the negative pressure has low peak value of the pressure, it sustains for a longer time. That is the botheration here. It can influence something called, this can influence something called debris motion. And it can cause secondary effects on structures. Okay. I can give examples. It can cause leak or cracks in joints, breaking of water or oil seals, breaking of window and door glasses, etc. So, they have secondary effects on structures, but that is also very undesirable in case of blast load analysis. Now, let us talk about the pressure time history impulse wave, which is given by this equation, which already we discussed in the lecture. So, now friends, the blast wave propagation is determined by blast pressure history. The variation of pressure at any fixed location away from the center of detonation is obtained by using the following assumptions. Number 1, shock wave due to explosion moves away from the center of detonation at a speed us. Now, when the shock wave reaches the point of arrival at time Ta, the pressure rises to P naught. The peak overpressure PSO, which is called the side overrun pressure or the peak incident pressure, is reached at this stage. The time needed for the pressure to reach its peak value is very, very small, and therefore, for design purposes, this is taken as 0. Look at this curve. After T0 is reached, it takes no time to reach the peak overpressure. Okay? So, for design purposes, this time is taken practically as 0. The overpressure decreases exponentially from its peak value to the ambient and goes to the negative side. You can see in this figure. It exponentially decays, touches the ambient, then goes to negative before it comes to ambient. So, the duration of the negative phase is much larger compared to the positive phase, and this can cause lot of secondary effects on structures. After the positive phase of the pressure time profile, pressure becomes smaller than the ambient value. The movement of air caused by shock waves induces dynamic pressure in addition to blast. So, therefore, friends, when the pressure wave is a negative phase, it induces dynamic pressure in addition to the blast pressure. Okay? So, look at this figure which shows me the exponential variation of the pressure with time, which will usually modify and model as linear equivalence. As linear equivalence in this case. Okay? So, it is modified and modeled as a linear equivalence, and I call this as time d, whereas the original time which takes for this is T naught. So, in this figure, T naught is the original time for the decay, but this is modeled as approximately as TD, which is a linear equivalence of this variation. Okay. So, it is a simplified representation of exponential overpressure in the structural system. So, friends, in this lecture, we learnt about the blast wave models, we also learnt about some terminologies related to the blast waves like standoff distance, working out the standoff distance for the front face, side face and the back face and top face of the building. We also computed something called the scaled distance if I know the standoff distance. We also learnt about the TNT equivalence, why TNT is considered as a referral explosive. We have also learnt about the pressure wave behavior, where it from ambience goes to the maximum, then drops down and becomes negative, comes to ambient. So, this phase is more dangerous, causing secondary effects. This phase gives you the maximum damage due to blast. So, friends, hope you have understood these sequel lectures again. We will continue to discuss more detail in the next lecture about blast resistant design of waves. Thanks to Bureau of Indian Standards for giving us support of these equations and theory related to blast analysis. Thank you very much. Namaste.